Okay, so then now we will have the next set of lectures, and it's a really great privilege for me to introduce the next speaker, or next set of our new lecturer, Edmond Iancu, Professor Edmond Iancu, who is in Saclay in France, which is an institute located in the middle of nowhere, which it's almost 1.5 hours by train from. But it's a wonderful place for doing great physics, and Edmond has made really fundamental contribution in the study of PQCD, low X evolution, which has become fundamental for understanding the initial state of the heavy ion collisions from where the Quark-Gluon Plasma gets formed, and his contributions is very well known in the form which we have here in the previous lecture. It's Jim-Walk evolution or evolution of Paton distribution in X at fixed Q square, and he's the eye of Jim-Walk. And this and he has not only developed this Jim-Walk evolution, he has also applied it with Jean-Paul Blazon and Tony Rabin in this audience and others to the study of the color glass condensate also. And recently, he has also done a huge body of work on understanding jets or jet quenching in the Quark-Gluon Plasma using perturbative QCD methods, and which has been well recognized in the community. And another great thing about Edmond is that he's also a very good mentor. He has mentored enormous number of young people and who are very successful in the field. And I was also honored that I was able to start a program of understanding of how to combine the initial stages of heavy ion collisions with a holographic approach, what we call semi-holography. And we were able to start, we started it together when I was in Saclay as a postdoc, and I learned a lot from him while working with him. I'm sure that you will also learn a lot from these lectures, and as I said, and as we mentioned before, and also Rajesh mentioned, you should also discuss with him after the lectures and not be shy, and I'm sure these lectures will be very enjoyable. So over to Edmond.
Hi everybody. So after Ayan's enthusiastic introduction, you all have much expectations from me, and I hope I will not disappoint you. So I'd like to thank Ayan and Sayantan for inviting me and for this introduction. And I like to lecture. Not the first time I'm lecturing these topics, although it's the first time I combined the two topics in a single lecture. That was somehow Ayan's suggestion and ambition to have from me both a talk on low physics and one on jet quenching. So this title was coined by him. It's not a bad idea after all, because as I try to argue what follows, these two problems that I'm going to discuss about QCD scattering at high energy or small x, and jet quenching and ultra-relativistic nucleus collisions, they do have something deep in common. They are both exploring the physics of high parton densities. And because of that, because of asymptotic freedom of QCD, they both can be approached via weak coupling techniques, which does not mean perturbation theory. Because precisely because of the high parton densities, one has strong nonlinear phenomena which require for non-perturbative techniques. But these non-perturbative techniques are mostly resummation of perturbation theory. So they're under control. We can do a lot of progress on first principles because we have asymptotic freedom and we look at dense systems. Dense systems are easier to deal with than dilute systems in QCD. So these two problems have profound differences in terms of kinematics, physical setup, and observables, but they have in common microscopic ingredients like multiple scattering and quantum evolution in strong background fields. I'll develop that once for all in the context of QCD scattering at high energy. Then I use the same kind of concept in the context of jet quenching. They also have in common various theoretical concepts and approximation schemes like gluon saturation, momentum browning, Acorn approximation that I'll introduce one after the other. The main topic of both lectures from the point of view of the theory of the PQCD is what is called parton evolution, and especially with increasing energy. It's the way how the wave function of a hadron develops when increasing, modifying the resolution scales at which one probes the hadron, the energy and the transverse resolution. And we will be led to consider both what's called space-like evolution, the one which is, for instance, probed in DIS via the evolution of the parton distributions. This is a cartoon of DIS, electron scatters of a proton by exchanging a virtual photon. The virtual photon can be absorbed by a quark, but this quark need not be a valence quark, can be product of a parton evolution chain inside the proton. I'll return that in a moment. It could be also what's called time-like or final state evolution, like in the example of electron positron annihilation. Then in that case, the virtual photon has positive virtuality. Here we have the negative virtuality. And this a positive virtuality object is an unstable object. It will decay. In the first approximation, it will decay in a quark-anti-quark pair, but they can be themselves time-like, and then they decay again and again. These are the jets. So this is the physics of parton distribution. This is the physics of jets. And in fact, for dilute systems, these two physics are deeply interconnected. They are the same physics by crossing symmetry. They both involve the declapsulating function. What is interesting, though, is that when going to dense partonic systems, this symmetry is broken. So the space-like evolution and the time-like evolution don't look the same anymore, at least not in the older situation. And of course, these are cartoons for space-like, these are for time-like evolution in the presence of multiple interactions of high parton densities. And explain these kind of cartoons would be the main purpose of the lecture. So far with the general introduction, now I start the first lecture, which is about the LOX theory. Now more precisely, dub high energy quantum chromodynamics and the Quark-Gluon condensate. And this is an event from a nucleus collision at Alice. You can see about 20,000 particles in the detector. So these are the final particles produced in a scattering between two lead nuclei at Alice. That's a real picture. It's a real event. And this is a theory cartoon. It explains the evolution of the wave function of a hadron with increasing energy or increasing standards resolution. And that, of course, is going to be explained by what follows. So the outline of this first lecture, I'm not going to read all that. There are 2 pages of outlines which you can use by yourself in order to see where we stand with the topic, with the evolution of the topic. I will start by a very general introduction in which I introduce the main idea in a simple setup, and then I will come back to these ideas and put them on a more firm basis by developing the formalism, first by introducing the kinematics, but then by defining the approximations, and eventually by presenting the effective theory based on this approximation, which describes this physics here. And all that is text, two slides of outline. For references, well, there are many references. I try to only select for you a few more pedagogical ones. First of all, I will rely on the previous lecture by Michael and by Raju, although I'll try to be as autonomous as possible, especially because there are students which missed the first week. So there'll be some overlaps and repetition with these previous lectures. For both my lectures of today, I have written myself a set of lecture notes based on the lectures on heavy ion physics I gave at the summer school at CERN a few years ago. So this is very basic. It's about 70 pages, but it's cartoon-wise. It's very hand-waving, so it's an easy first lecture. And more specific for the lectures of today on QCD at high energy, there are more detailed, more advanced review papers. There is an excellent textbook by Yuri Kovchekov and Eugen Levin. And there are some review papers devoted to Quark-Gluon condensate physics. And these are the list of them. There are other ones. I will try from time to time to also give references on my slide, but most likely I will forget to do that. So don't hesitate to ask me or to look for the references in this lecture. Okay, so I will just start with a few slides of motivation. These are 2 kinds of experiments of processes that I'm going to use to illustrate the theory. So I'm not going to discuss phenomenology in great detail, but I will use the example of what's called dilute-dense scattering in order to build up the theory. What means dilute-dense? Well, I have 2 examples, then I'll explain to you why they are dilute-dense. The 2 examples, one of them you're very familiar with it, is deep elastic scattering. I already mentioned it before, a virtual photon with negative virtuality, which I'll denote the modules of the negative virtuality. It is traditionally denoted by Q squared. And the other independent variable for DIS is Birken X, the ratio of Q squared and essentially the energy S of the proton plus virtual photon system. And we're interested in the high energy or small x regime where this variable X is much more than 1. And already from the previous lectures and from your general culture on particle physics, you know that the Birken X has a very simple interpretation, at least in a specific infinite momentum frame and a specific gauge. It represents the energy fraction of the parton, of the quark, from the proton, which absorbs the virtual photon. So in DIS, we have a very direct mapping of the kinematics of the collision onto the parton structure of the proton. Q squared, the resolution of the virtual photon, give us the area in transverse plane onto which you probe the partons. And X, the Bjorken X, gives us the energy fraction carried by the parton. And the same mapping also occurs in another system, which is of interest for the physics at the LHC. It's called proton-nucleus collision. It's one of the hadronic scattering processes which is studied intensively at the LHC. In this case, we scatter a proton of a nucleus, and one is measuring particle production, say in the what's called forward direction, which means in the direction of propagation of the proton projectile. And the rapidity variable eta, it measures the propagation angle of the produced quark, in this case, with respect to the collision axis. Eta positive means a quark which is produced in the same direction of motion as the incoming proton. And the relation between the kinematics P perp eta of the produced quark or hadron and the energy fraction of the gluon from the target which is interacted is given by this value, by this expression here. So you see again that in the region where the energy is high, the energy S of the proton nucleus scattering, much higher than the transient momentum P perp of the produced quark, and also in the region where the produced quark is produced at 4 rapidity, so at eta positive, in that region X is much more than 1. So once again, this process here probes the small x component of the wave function of the target. So the target is proton in DIS, and it is nucleus in PA, and the projectile is virtual photon or lepton, if you want, in DIS, and it's a proton in a PA. And what is specific is that when you go to small x, and enter the proton here or the nucleus there, one sees a dense system of gluons. I'll show you why in a moment. And in order to measure the property of this dense system of gluons, it is convenient to use a dilute projectile as a probe. So the virtual photon here and the proton here are just thermometers, which are measuring the properties of the gluon distribution inside the proton in DIS or inside the nucleus in PA collisions. So our main physics interest will be about these dense gluonic systems, and these two processes here, which are called dilute-dense, because the dilute projectile scatters for dense system, dilute projectile for dense system, will be used as a way to extract this information about this dense gluonic system in the experiment. And they're both widely measured experiments. So, you may, I just mentioned before that you're interested in the physics of dense gluonic system, but you may argue that the virtual photon in DIS cannot couple to gluon directly, it couples to quarks because only the quarks have electric charge, and that's true, but that's a bit of a triviality because the virtual photon couples directly to a quark or to anti-quark, but this can be a final product of a chain of parton evolution inside the proton wave function, and this chain of parton evolution also includes gluons. So the gluons are measured indirectly via their effect on the quark distributions. The quark which is scattered can be a valence quark, but can be also a C quark as produced by the decay of a gluon. And in fact, in the small x kinematic of interest here, we're about sure that this small x quark here is not a valence quark, because valence quark carry a large fraction of the energy of the proton, like 1/3. This is necessarily a C quark. So in fact, this quark here is more or less a quark like this one here, produced by a chain of evolution. So in fact, this evolution also is probing the gluons indirectly. Well, what I mean by quantum evolution, just to be on have a clear definition, we understand the change in the partonic content of the hadron wave function when changing the resolution scales, x and q squared of the experiment, and this change occurs due to additional radiation, to the fact one can add more and more ladders in this chain here when changing x and q squared at the endpoint of the ladder. Now, the data, this is the data at Hera for the parton distribution functions, the C quark distribution function as a function of x. X goes like that, so x is 1 here, x goes more here. And the gluon distribution, xg, and also the C quark distribution, xs. And you see at small x, below 10 to minus 2, essentially all the partons are gluons or C quarks. The valence quarks decay. They're not there anymore. So what I said before, the quark which is struck in DIS is a C quark, and moreover, this C quark is simply produced by a gluon, and so essentially the typical evolution of small x is it's a ladder which contains essentially only gluons, except for a very, very last step where you need to produce a quark, otherwise we have no DIS. So this is just the data. The data are telling us that that's a perturbative picture of the gluon, of the proton, sorry, a small x. And of course, we like to understand this picture behind this cartoon. We like to transform this cartoon into a Feynman graph, and we like to compute it. Right? Okay, so, but the moral, which is going to be developed in what follows, is that the gluon distribution is rapidly amplified by the quantum evolution with decreasing x or with increasing energy at 6q². And why is that? Well, it has to do with radiative processes, with Bremsstrahlung. So let me introduce Bremsstrahlung. Well, you certainly know what Bremsstrahlung is, but just let me fix notation and let me show what I need out of the Bremsstrahlung. Because at small x, we do need only very little out of the generic Bremsstrahlung. So I'll start with the generic Bremsstrahlung for emitting, say, a gluon out of a quark. A longitudinal quark with longitudinal momentum pz, zero transit momentum, radiates a gluon with longitudinal momentum fraction with x, so longitudinal momentum kz, which x times pz, and which carries some transit momentum k perp. And of course, by energy momentum conservation, the recoiling quark has an energy momentum, a longitudinal momentum 1 minus x times pz, and a transit momentum minus k perp. And now, this diagram, there's an amplitude, you take the modulus squared of it, it gives you a probability or a spectrum for emitting this gluon, and the differential probability, delta p, for emitting a gluon with x between x and d by d, x plus dx, and k perp between k perp and k perp with the dk perp, is given by this formula here. It's on order alpha s because of the square of the vertex here, has a color factor CF, again, because of the thematics for the quark in the fundamental representation. And most importantly, it has a dependence on the k perp and x of the emitted gluon. The x dependence is included in what's called the Diglap or the Altai-Parisi splitting function, in this case for the splitting of a quark into a gluon with a gluon carrying the fraction x of the quark. And the transit momentum dependence is encoded in this factor here, which is divergent when k perp goes to 0. And more generally, this factor here shows a logarithmic enhancement over all the range in k perp. Now, this Bremsstrahlung spectrum has two essential features for what follows. It is divergent, it is logarithmic in both in transit momentum and in energy fraction 1 over x. Consider first the transit momentum. The typical k perp of this gluon here has to be bigger than lambda QCD, otherwise this gluon will be hadronizing. So we're only interested in PQCD, so we will not consider transit momenta below lambda QCD. It has to be much bigger than lambda QCD to be computable. And it is bounded in DIS by the virtuality of the photon. I'll show that in a moment, but in any case, the photon, in DIS, the photon can only seize fluctuations k perp up to q². In DIS, q², it's huge as compared to lambda QCD. It's of order 10 GeV, Q is of order 10 GeV or larger, when lambda QCD is of order 200 MeV. So we have a huge interval for logarithmic evolution between lambda QCD, I don't simply a lambda squared and q². This is a large log. We have a log enhancement for gluon emissions anywhere in the interval between perturbative physics and the DIS resolution. Moreover, we have also a logarithmic energy interval. So interval coming from the integration over x, dx over x. At small x, the numerator here is irrelevant, becomes 1, but the denominator is exploding, giving us a logarithmic integration. The lower cutoff comes again from the kinematics of the collision. It's set up by the DIS kinematics. The upper is Berkan excipient, and the upper limit is 1 because that energy fraction can be bigger than 1. So we have a logarithm 1 over x0 from the energy integration. I do not have y0 because it's typical notation, and the logarithm of q² divided by lambda squared from the transverse momentum integration. So these two logarithms is called transverse or coordinate logarithm. This is called energy or small x logarithm, the hallmark of the Bremsstrahlung. And because logs can be big, the kinematics is wide enough, they have to be resummed in perturbation theory. And that will be the purpose of the lecture. Now, if you look at the emission of the quark now, you see that the emission of the soft quark is not enhanced. A soft quark, it means that the energy fraction of the quark psi, which is 1 minus x, is much more than 1. When psi is much more than 1, you just replace x by 1 minus psi. You see when psi is much more than 1, there is no divergence at psi equals 0. So the Bremsstrahlung is only enhancing the emission of soft gluons. On the other hand, the transverse enhancement is present both for quarks and gluons, because the K-perp here is the same by energy moment conservation. So the Bremsstrahlung or PQCD evolution has a coiner phase space for all the partons, but has a soft or infrared phase space only for the gluons. And now, if instead of a quark here, you have a gluon incoming particle, then the gluon can split into two gluons, or into quark-antiquark pair. The quark-antiquark pair is not going to be important because the quark-antiquark pair is not going to develop the infrared singularity, but it does has but the gluon pair has the infrared singularity. So if a gluon goes into two gluons with energy fraction x and y minus x, then there is again the coiner singularity, transfer momentum, and there is also the infrared singularity when any of the two gluons is very soft, or either x goes to 0 or 1 minus x goes to 0. Of course, there is a symmetry between the two gluons, x going to 1 minus x, so it's good enough to define the soft gluon regime as x much more than 1, because the other case, when 1 minus x is much more than 1, can be treated by symmetry. So from no one, soft gluon for me is going to be x much more than 1, which means one is soft, the other one is hard. So in this soft regime, one can simplify the gluon-to-gluon splitting function, that's the generic version of the de Graaff splitting function. But when x is much more than 1, you see that, again, the numerator is irrelevant, and in the denominator, can keep one more x only. So the probability, the differential probability for a gluon to radiate a soft gluon, remain the origin 1, has this simple form, the polar factor times alpha s, the logarithmic phase space for the transverse integration, and the energy or x phase space for the longitudinal integration. Now, this gluon by itself can emit an even softer gluon, and so on, and this multiplication of the gluon via softer and softer gluon emission is the basic mechanism for the high energy evolution. To understand a bit better the space-time picture of the high energy evolution, we have to have to understand what the notion of the formation time, what the lifetime of the fluctuations. So let me make a short digression of what the lifetime of fluctuation is supposed to be. So this is, if you want, the same kind of diagram as before. If this gluon here, if this gluon here was space-like, then it cannot decay onto two on-shell particles. It can create a fluctuation, but the fluctuation has to close back eventually. And the lifetime of the fluctuation is essentially the typical time between the emission and reabsorption of the photon. If the gluon was time-like, it could decay, but in that case, it would take a time before it decays. So in that case, I don't not speak about the fluctuation lifetime, but about the formation time for the fluctuation. Both are given by the same formula. In this case, I'm focused on part on this evolution, so it's a space-like situation, so I will discuss this as lifetime of the fluctuation. In my second lecture, I will speak about time-like evolution. I will have time-like partons, and the same formula I will give in that case. I will show you in a moment, at that moment the formation time, the time it takes for the gluon to split to gluon. But let's focus now on the language of space-like evolution. So an on-shell parton or a space-like parton cannot decay into a pair of on-shell partons. The gluon is emitted and eventually reabsorbed. It's a virtual fluctuation. And how can one estimate the lifetime of this fluctuation? Well, if the gluon has to be reabsorbed, it cannot separate too far away from the quark, not farther away than a transverse wavelength lambda perp, which is 1 over k perp, 2 over k perp conventionally. So, because if the separation between the gluon and the quark were larger than the transverse wavelengths of the gluon, then the gluon and the quark would totally lose any quantum coherence. They will not overlap anymore. And if that's possible, then the gluon is escaping. But it's not possible by energy momentum conservation because we're in this space-like situation. So the gluon can separate from the quark up to that distance and then has to bounce back. So in a time delta t, which is the lifetime of the fluctuation, the separation delta x perp between the quark and the gluon, they call it delta x perp, which can be estimated as the time delta t times the transverse velocity of the gluon, which itself it's the transverse momentum of the gluon k perp divided by its longitudinal momentum kz. So the transverse velocity times the delta time should be smaller than the transverse wavelength, which is 2 over k perp. By putting together this, by just extracting delta t from here, one sees that the maximal lifetime with the fluctuation delta t is twice kz divided by k perp squared. Since kz is x times pz, in the terms of the energy fraction, the same as twice x pz divided by k perp squared. This is a simple formula to understand. If you can imagine this factor kz divided by k perp squared as the product, if you want, of kz divided by k perp times 1 over k perp. If the quark was at rest, then kz on k perp would be comparable, and this would be for the 1, and that would be the only momentum scale in the problem. So the lifetime of the fluctuation will be the inverse of the momentum. That's just uncertainty principle. If the quark is boosted to a large longitudinal momentum kz, then this is just the gamma factor, which is much bigger than 1. So the lifetime in a boosted frame is the lifetime in the rest frame times the boost factor. And the same estimate can also be obtained more formally from the uncertainty principle, the energy denominator. I will let that as an exercise. So now this is generic information about fluctuations. Let me apply that to the case of DIS to understand a bit better the resolution of the visual photon in DIS. So this is the formula for the lifetime of this gluon fluctuation with longitudinal momentum x, fraction x, and transit momentum k perp. If k perp is hard enough for a given x, this delta t can be arbitrarily small, but very hard fluctuation live very short cannot be probed by the scattering. A fluctuation can be only probed by the DIS if it lives long enough to overlap with the scattering process. So the lifetime of the fluctuation delta t should be bigger than a collision, the duration of the collision, delta t collision, which is essentially the inverse of the energy of the photon, because that's only scale for the energy of the collision. So the condition that delta t be bigger than delta times the collision, together with this expression for delta t, is and recalling the expression of x in terms of q squared and s, can be easy combined together to see that the only fluctuations in the proton wave function that are measured by DIS are those whose transverse momenta up to the virtuality of the photon. So as I was saying before, the virtuality of the photon sets up the scale for the transverse virtuality. And the parton distribution as measured by the DIS are just the number of partons with any transverse momentum up to q squared. Those with higher transverse momenta, they live too short to be seen by DIS. But those with lower momenta, they have long lifetime, much bigger than collision time, so they can scatter. And by the uncertainty principle, the transverse momentum, say a parton with transverse momentum up to q squared is delocalized in a transverse plane in an area delta x perp squared of order 1 over q squared. So that's the size of the spot seen by the visual photon. A visual photon with a given q squared sees a spot in the proton of area 1 over q squared, transverse area 1 over q squared. So now that we have an understanding what the parton distribution are supposed to be, and also how the gluons are produced via Bremsstrahlung, let's make as a first exercise the simplest possible calculation of a parton distribution is that of the gluon distribution as produced, say, by a quark. A proton will be just 3 valence quarks, so this should be just one of the valence parts of the proton. So we like to compute how many gluons. The gluon distribution is a number of gluons with a given energy fraction x and any transverse momentum up to q squared. That's the notation. So I want to compute how many such gluons can be produced by a quark. And I will start that by lowest order PQCD. So at lowest order, we have only one gluon emission, a gluon with a given x, which is fixed because we fix the value of x, and some k perp is emitted according to the Bremsstrahlung law. That's the Bremsstrahlung law here. So the number of gluons is the same as the probability I shown to you before, because we're having only, we're having only one emission, so the probability for one emission is the same as the number of emissions. Once we're going to have more than one emission, the number and the probability will not be the same anymore. But so long as I have a single emission, the probability for that emission and the average number of the emitted particle are the same. So this delta P here is also the delta N, the spectrum. So I'm going there now, and I compute. So this is the spectrum, the number of gluons per unit x over k perp given by a single emission by Bremsstrahlung. Is the alpha s times the color factor, 1 over x from the infinite singularity, 1 over k perp squared from the collinear singularity. And I integrate over all the k perps up to q squared, and I multiply by x, because multiplying by x is a part of the conventional definition of the gluon distribution. So you see what happens. The integration over k perp squared produces a log from lambda qc to q squared. So the number of gluons grows logarithmically with a resolution scale at the beginning of the Diglap evolution. Also, the number of gluons times x is independent of x. Why? Just because it was 1 over x in the spectrum and I multiply by x, so by is trivially independent of x. That's the property of gauge interaction. And it is also logarithmically sensitive to the confinement scale. So this study is not infrared safe. We count the number of gluons. The number of gluons is not a well-defined observable. So whenever you have infrared unsafe observables, we are eventually sensitive logarithmically, typically, to the non-perturbative scales. But our main purpose is to study the dependence upon Q squared, to take a derivative if you want. And if you take a derivative with respect to Q squared, the dependence upon lambda disappears. So, but that was just the leading order result, one gluon emission. And I mentioned to you before that once you emit a gluon, this gluon can emit another one, and so on and so on. So although we want to measure just the gluon at the value of x, let me consider a process in which along the way, I emit another gluon with intermediate x, x1, between x and 1, which is not measured, because I only measure as a given x. So the external x is 6, right? The external x is 6 here. But my last gluon may very well not be emitted directly by the quark, but it might be emitted by an intermediate gluon with a function x1, which is not measured, which should be integrated over, and which was then itself emitted by the quark. This intermediate gluon has a x1 between x and 1, has an intermediate k1 perp between k perp of the final gluon and lambda QCD, which is again not measured. So now this process here is a perturbative coefficient of the previous one, because I have 2 more factor of g. So I have, sorry, when I take the probability, sorry, I have 1 more factor of g, and I take the probability, the square, I have one more factor of alpha s. It's a higher order effect. But so you see, I have 2 powers of alpha s. The alpha s from the first emission here with a CF, and the alpha s for the second emission with the NC, because it's gluon emitting a gluon. I use magenta for the intermediate gluon emission, so x1 and k1 refer to the intermediate gluon, while blue one is for the final gluon emission. So for the given kinematics x and k perp of the final gluon, I have to integrate over x1 from x to 1, over k1 perp from lambda to k perp. And once I did do that, I also integrate over k perp from lambda QC to q squared, because I don't measure the k perp of the final gluon, only the resolution. And this intermediate integration over x1 and k perp 1, we have 2 logarithms, so give me a logarithm of the transverse resolution scale times logarithm 1 over x with a factor 1/2. And this is the radiative correlations, the log square times an alpha s, on top on the leading order result. So I have recognized here the leading order result, which contains alpha s here from here. And this is the additional factor coming from the emission intermediate gluon. So I have radiative correction, G1, which is suppressed with respect to the leading order result by a factor alpha s, but is enhanced by a double logarithm, a collinear one and an energy one. And as you can imagine, if the logarithms are large enough to compensate for the suppression of alpha s, this effect is of order 1, and this seemingly one-loop correlation is of the same order as the leading order result. And when this happens, I have to consider farther and farther emissions. I have to consider an arbitrary number of emissions, 1 to up to n, where the n being up to, and the n plus 1 is one I measure. So in order to have a logarithm of energy for each emission, and also a logarithm of transverse momentum for each emission, I have to ensure that the successive emissions are strongly ordered in x. So x is much more than xn, which is much more than xn minus 1, also, and so on up to x1, which is much more than 1. And an inverse ordering in transverse momenta. The final gluon is the one which you probed in DIS, has a higher scale perp of QS. The previous one has a smaller k perp, and the previous one has an even smaller one, and the first one can be as soft as lambda QCD, at least. So I have a succession series of n emissions, strongly ordered in energy and in transverse momentum. When I integrate over the energies in this chain, I get 1 logarithm of energy for each integration. I have n integrations, but I also have a factor 1 over n factorial because I have to order them. Similarly, when I integrate over the transverse momenta here, I have a factor logarithm of q squared that I denote rho for each emission, rho n, but I also have to order them, so I have another 1 over n factorial. And of course, I have a factor alpha s for each additional emission, because I have a factor of g in the amplitude per emission, and I take the square, I have an alpha s for the amplitude. So altogether, this cascade itself gives a factor alpha to power n for vertices, y to power n divided by n factorial for the energy integration, and rho to power n divided by the n factorial for the transverse momenta integration. And this n is arbitrary because I can have a cascade with 0, 1, 2, or arbitrary n gluon, intermediate gluons between the quark, which is the source of the evolution, and the final gluon that I measure. So overall, the total gluon distribution, which is the sum of all the possible cascades with any number of intermediate gluon, is given by this version. this expression here, the gluon distribution with the evolution included in this double logarithmic approximation is the same as at leading order times the sum of all intermediate cascades from any number of intermediate gluons. Each cascade with n gluons has this particular factor, so contribution. So I have a sum of this series. This is a very simple series. Even myself, I can sum it. It's just a modified Bessel function of rank 0. That's not important. This series is so important. It's so easy to deal with that even without knowing what the Bessel function is. One knows what are the properties of this solution here. And in particular, if one goes in the we're interested in a regime where these logarithms are large, where alpha y rho is bigger than 1 or of order 1. Otherwise, we could truncate the series to a finite number of terms. But we're interested in the high energy regime, so the small x or large y. We're interested in high q squared DIS or large value of rho. And then alpha y rho is of order 1. This series has to be resummed. And in particular, if alpha y rho is much bigger than 1, one can use the asymptotic expansion of the Bessel function, and one can reduce that for very large y and rho, such that alpha y rho is bigger than 1. The gluon distribution has a rapid quasi-exponential increase with y and rho. So it's exponential of 2 square root of alpha y rho. So it goes like square root of y, logarithm y raised. It also goes to square root of rho, or logarithm of q squared over lambda squared. So it's a rapid increase both with decreasing x and with increasing q squared. And that's the Diglab evolution. It's the small x limit of the Diglab evolution. The Diglab evolution does not assume small x. It has full splitting function. It's more complicated, and one cannot write a simple expression like that for the Diglab evolution. One can solve it numerically, one knows how it works, but one cannot write a simple analytic result. But in this double logarithmic approximation, where one takes simultaneously small x and large q squared simultaneously, then one can resum the series to all orders, because the leading approximation is this double log approximation, which is very simple. And this is a generic result which illustrates more complicated evolution. Okay, and now I return to the physics of DIS. So we're in the small x regime. We know this is the proton, this is the valence quarks. Each of the valence quarks acts as a source for gluon cascades. And one of these gluon cascades eventually produces a quark-antiquark pair, which absorbs the virtual photon coming from the DIS. So the virtual photon scatters over C quark, or C quark-antiquark pair in general, which is a final product of a gluon cascade. And this is in agreement with the fact that, as seen at Hera, the gluon distribution grows very fast. In fact, one can parameterize the data at Hera. Again, this is just measurement. One can show that the data at Hera show a rapid increase as a power 1 over x. The gluon distribution at Hera as small x grows essentially as a power 1 over x to power lambda, where lambda is an exponent of order 0.2, which depends slowly upon q squared, but value between 0.2 and 0.25 are valid for any q squared, so long as x is small enough. So we have a rapid, explosive, power law, exponential in rapidity growth at small x of the gluon distribution. This is a property of PQCD, and it's a property of the data. Now, the question is, can this rise go on forever? I mean down to arbitrary small x. You may say the number of gluons is exploding, and so what? I mean, the number of gluons is not a physical quantity. If you ask the question how many soft gluons, or even how many soft photons you have, the number is infinite for good reasons. So that's not a problem. Having infinitely many soft photons will not pose a problem to nobody. Having infinitely many soft gluons does pose a problem, though, because gluons can interact with each other unlike the photons. So having very, very many gluons, one can start having a nonlinear system. And that's what I'm trying to argue on the next slide. So far, we have assumed that the gluons are just emitted and then they're lost in the nature. They're part of the wave function. They remain inside the proton. They're emitted, they accumulate inside the proton, but they don't see each other. Why they don't see each other? Because look at this cascade, they're linear. Each gluon is emitted, but this gluon and that gluon don't interact with each other, right? So that was the assumption behind this calculation here. We assume that emissions are independent from each other. Each new gluon acts as a source for another one, but it does not, the products of it does not interact with the other one. So gluons indeed don't interact if they don't overlap, and vice versa. If they do overlap, they then do interact. So for the gluons to interact with each other, they have to overlap with each other. So let's try now to have a physical picture of the evolution in terms of the wave function of the proton. Again, we have the proton here. It's a Lorentz contractor because we're in this frame in which the proton is highly boosted, has a large gamma factor. So that's a proton. This is supposed to be the 3 valence quarks. And this is some gluons which are radiated by the valence quark. Right? The proton has a radius r in the transverse plane and a radius r over gamma in longitudinal direction with gamma big. At LHC, gamma is of order 1,000. So this distance is 1,000 times more than that. The valence quarks are equally boosted, but the longitudinal gluons are not that boosted because they have small values of x, which means they're delocalized in the longitudinal direction. So by the uncertainty principle, a gluon with transverse momentum k perp occupies a transverse area 1 over k perp squared. And if it has a longitudinal momentum kz, it has a longitudinal extent 1 over kz, which means 1 over xp, which is large at small x. So the small x gluons are delocalized around the hadron. And there's no contradiction with confinement because the confinement acts is a vacuum scale. Confinement acts on a scale which is lambda QCD, and 1 over lambda QCD is like from here to here in this scale, right? So if you're on the lambda QCD, what is on this scale, but this is much more than that by a factor of 1,000. This figure is not at the scale. So small x gluons are delocalized in longitudinal direction, and because of that, they can easily overlap with each other with longitudinal direction. If you look in this direction here, all the gluons overlap with each other. This one and that one and that one, they all overlap. But on the other hand, they also occupy a transverse area and transverse momentum. This transverse area is supposed to represent, see, the height of this wave here. The transverse plane goes like that. So the width of this wave is a transverse area. This is a very large gluon, has a small k perp. This is a very small gluon, has a larger k perp. But in this figure here, none of the gluons overlap with each other in the transverse plane. So these gluons do overlap in the longitudinal direction. They do not overlap in the transverse plane. They do not interact with each other. The same happens here. You see, I'm doing the evolution. I'm producing more and more gluons. They have, and I do the same as before, the double logarithmic or diglap evolution. I produce more and more gluons, which have smaller and smaller longitudinal momentum fractions, so they are more delocalized in the longitudinal direction. But they also have larger and larger k perp, so they are smaller and smaller in the transverse plane. They're more and more punctual in point-like in the transverse plane. All these gluons do not overlap with each other. So this diglap evolution, in fact, maintains a dilute system of partons. We have more and more partons, but there's more and more transverse size, and they don't overlap. So in that sense, the diglap evolution can go on forever at arbitrary small x if one at the same time increases q squared. What is more interesting for us here, though, is a different evolution. It's called BF-Keil evolution, in which one is decreasing x at roughly fixed k perp. This is not diglap. I'll tell you how this comes out in a moment. In that case, one is losing the logarithm of transverse resolution. One only has logarithm 1 over x. One has to sum logarithm 1 over x to all orders. In that case, you see, these are again 3 steps in the evolution. At the beginning, I have a few gluons with some values of x and some values of the transverse momenta, some area. Then I decrease the x, so I produce more and more gluons, which are more and more delocalized. But I keep their transverse momenta fixed, more or less. They have more or less the same transverse area. This area here, this area here, and this area the same. When I keep adding more and more gluons with more and more values of x in the same area, since they occupy all of them the same area on the transverse plane, and the gluons are not smaller and smaller, they are bound to overlap with each other eventually. So here they don't overlap, here they barely overlap, and here they strongly overlap. See this gluon, and that gluon. They overlap both the longitudinal direction and the transverse direction. The same, these 3 gluons here, this and this and this. They overlap in both longitudinal direction and transverse direction. These 3 here, this and this and this. They overlap both longitudinal direction and transverse direction. Gluons which overlap with each other in phase space, meaning simultaneously longitudinal and transverse direction, can interact with each other. And when they interact with each other, they repel each other. So they cannot be added ad infinitum. So this physics of the mutual interaction of the gluon was missing in the linear evolution I showed to you before. And that evolution has to be amended eventually when the gluon density becomes large enough. Now, the question is, what is the relevant measurement of the gluon density? And I'd like to ask you that the relevant measurement is provided what is called the gluon occupation number. And that's the same occupation number that Søren introduced in his talk. It's just the number of partons here of gluons per unit in phase space. Unit phase space means 3-dimensional phase space, which is 3-dimensional momenta and 3-dimensional coordinates. In the relativistic setup, there is a distinction between longitudinal direction, the cohesion axis, and the two transverse directions. So the transverse phase space is the same as before, d2k perp for the transverse momenta, d2x perp for the transverse coordinate. You see, if you look at this as the size of a proton, and this is some parton inside, some gluons inside, This is the transverse area of the proton, and this is the transverse position x-perp of this gluons or quarks here. The longitudinal phase space is a bit more subtle. Should be dx, dkz. Dx is the same as dkz because x is energy, is a longitudinal momentum fraction. But instead of having here dz, we have x. Because why? Because all the gluons, we measure gluons with a given value of x. So all the gluons have the same x, and we multiply by x to simulate the longitudinal extent of the target. So this is a proper definition of the Paton gluon occupation number at high energy. There is some additional decorations. The 2 pi cube comes from the definition of the phase space for the momentum integration, and we divide by the number of colors, nc squared minus 1, and by the number of spin, too, because we want to count the gluon occupation number for gluons of a given color or of a given spin. That's the proper definition of an occupation number. Okay, so that's the definition of occupation number in full generality. How do we estimate that easily in view of what we have developed so far? The gluon occupation number is essentially the packing factor in the transverse plane. So I said before that xg of x and q squared is a total number of gluons having a given fraction of x, like here, and having a transverse area of q squared. Each of these 1 over q squared, each of these gluons occupy this area, 1 over q squared. So if you multiply the number of gluons by the area of a single gluon, you find out what the total area occupied by these gluons. And then if you divide the total area occupied by all these gluons by the area of the proton, you find the overlapping factor, the packing factor. Notice that the total area occupied by the gluons can be larger than the area of the proton because the gluons can overlap with each other. So long as this packing factor is more than 1, gluons don't touch with each other. So the total area occupied by this 6 gluon, you can add the area is more than the area of the proton. It's the same here, the same here. The decoupled evolution consists in going to more and more partons, which have higher and higher q squared, so they're smaller and smaller. There are many of them, but the area they occupy is very small. In fact, the more you go in the decoupled evolution, the smaller area you occupy. So although you have a system with more and more partons, the system is more and more dilute. On the other hand, if you go in this high energy evolution, you decrease x at fixed q squared, you produce more and more partons with having the same area. So eventually they occupy the whole space at their disposal, and eventually they have to overlap, because when the total area occupied by the gluons becomes larger than the area of the proton, which means that when the occupation number becomes bigger than 1, they have to overlap. And that's just an estimate, but we know from Hera that the gluon distribution grows as the power 1 over x. So if you just believe that and we put that in the simple estimate, then we conclude that the gluon occupation number grows as small x as a power. So if you go to sufficiently small x, the gluon occupation number, according to this linear dynamics, can become arbitrarily large. And when it becomes very large, large enough, the gluons overlap and they start interacting. Now, we assume that the density is so high that the coupling is weak. We'll return that in a moment. But assuming that to be the case, if the coupling is weak, although they interact, their interaction is spread by alpha s. So if the occupation number is of order 1, the interaction of order alpha s is still a small effect. But that would be the case here. But if the occupation number is as large as 1 over alpha s, then the 1 over alpha s from the occupation number can compensate the alpha s from the strength of the interaction, and the whole effect of the self-interaction becomes of order 1. That's the interesting regime, where the gluons are so strongly overlapping with each other that the effect of their self-interaction is a non-perturbative effect. They're weakly coupled, but there's so many that the global effect of the interaction is an effect of order 1, and still for order 1 have to be computed exactly into all orders, because small powers of alpha s here means small powers of alpha s there. So that becomes a nonlinear dynamics, and of course that would be the purpose of the lecture. Now I just introduced the basic idea. The basic idea goes long back, like 30 years ago, thanks to these people. The idea was that when the gluon occupation becomes as large as 1 over alpha s, then different parton cascades start to interact with each other. We have this kind of gluon recombination. From 2 gluons, you go to a single one, and this single one is measured, say, in DIS. So gluon recombination processes, 2 gluons go to a single gluon, become as important as gluon splittings, 1 going to 2, and they somehow equilibrate with each other. We go to like a dynamical equilibrium in the same way as we have chemical or thermal equilibrium by detailed balance. Here we have again a kind of detailed balance between recombination and splitting, and this keeps the occupation number at values of order 1 over alpha s. And that this regime here is called saturation. Why saturation? Because the occupation number saturates at order 1 over alpha s. And the whole purpose is to understand the transition between dilute system and dense system according to this barrier, which is called saturation line. And that is going to be described by a nonlinear version of the BF-Kyle evolution, which includes this recombination if you want into account. And that's the nonlinear BK and GMOC equations. That are going to be the main purpose of my first lecture. So now, before even going to these sophisticated equations I will introduce later, this basic idea here naturally introduces a typical scale, what's called saturation scale. In this, you see, I use here double logarithmic units, logarithm Q squared and logarithm 1 over x. So this, in these double logarithmic units, this is going to be a straight line. So what is the saturation scale? It's a typical transient momentum scale at which the occupation number becomes for the 1 over alpha s. We have this occupation number. It's a function of x and q squared. It's the number of gluons with a given x and q squared divided by the area of the proton times the area 1 over q squared of a single gluon. And we like this to be for the 1 over alpha s when the nonlinear effect becomes important. This is a condition for q squared as a function of x. You can solve this condition and just give a function q squared as a function of x, which is just the solution to this equation. In fact, if you use the estimate coming from the data for the gluon distribution with growing like a power 1 over x, then this condition that the occupation number be 1 over alpha s reduces to this constraint here. And using xg of x as 1 over x over x, essentially is telling us that this intrinsic scale saturation momentum squared itself grows as 1 over x to power lambda s. Lambda s is essentially pointing. So this scale, it's essentially it's a density of gluons in transverse area, because to obtain that scale, it's a momentum scale. It's dimension-wise, it's a momentum scale squared, but it's the same as the number of gluons per unit transverse area divided by the number of colors and times alpha bar. And since it depends upon 1 over x as a power law. If you take the logarithm of q squared here and logarithm 1 over x is there, you see that the logarithm of q squared is this power lambda s times logarithm 1 over x. So it is a straight line which grows with the energy was decreasing x. So this is the scale in energy at which the system becomes saturated as a given q squared. On this q squared, which is here, the system is dilute before that scale in rapidity and is saturated on higher values of y, which means more x. If I go now to a higher q squared, the system is much more dilute to start with. So on this size, transverse size, to have saturation, I have to go up to higher values of y, or it means more value of x. For each value of x, q squared is a value of q squared at q squared of x is a value of q squared at which I have saturation. So this saturation line, it's a fundamental scale because it's separated between dilute physics and dense system. And it's also the typical transverse momentum of the gluons at saturation. In particular, the interactions between these gluons are controlled by the coupling constant of QCD, the running coupling of QCD, at the scale which is q squared s itself. So if energy x is small enough, q squared of x is large enough, and if it is much larger than lambda QCD, alpha s of q squared s is much more than 1, and then I can apply PQCD to describe this wave function. So that's the ultimate justification for the procedure. I started by assuming PQCD. That's correct if I have a dense system, and I just convinced you that the high energy evolution QCD is producing a dense system. A dense system needs a scale which controls the density. Being dense meaning that scale is hard. In this particular case, that scale is saturation momentum squared. It's a density because it's a number of gluons per unit transverse area, but it's a momentum scale. And this momentum scale being hard means the system is dense, means the coupling is weak, means I can study this system in perturbation theory, means that the whole argument I used so far with alpha s more than 1 so on was consistent. Of course, that may not be right for the phenomenology. It might be that the value of x at which q squared of x is much bigger than lambda QCD is tremendously small, but it's probably not the case. Probably we're lucky enough to be in this regime of nonlinear dynamics and saturation at the energy of LHC. Good. Let me see what I have. Yes, questions. So that was the end of the general introduction. So if you have questions at this level, that would be a good point. So good point for me to rest. Yes, please.
Is becoming possible.
In fact, precise. It's a very, very good question. First of all, the gluon combination, it's a hand waving. There's no gluon recombination in reality. The repulsion mechanism works as a nonlinear effect, which is more complicated than gluon recombination. But at the level of this cartoon discussion that was given in the 80s, gluon recombination was precisely the repelling mechanism. So, yeah, I know it sounds counterintuitive. That was limiting the gluon repulsion. It's a more modern concept. At that time, they were imagining this saturation as a dynamical equilibrium between two competing processes, splitting and recombination. Now we understand it's more complicated than that. The gluon recombination picture is not the right picture, and the right picture is hidden in the words gluon repulsion, but that's not obvious in this cartoon. So that we have to wait for. That Zimok equation, all that. This is just a cartoon. This is not a Feynman graph for the time. So the mathematics is much more complicated. But that's why this is an introduction. So the main purpose will be to explain to you the correct version of this physical picture as coming from the modern correct equations. And in that case, the notion of gluon repulsion makes sense, while the notion of gluon recombination does not make sense anymore. So, but it's a very good question. It's a deep question. So I cannot enter the details here.
I want to know if I understand it correctly. As per D-glap evolution, the gluons don't overlap,
Yes.
and thus they are able to generate the quarks.
Yes, the quarks, sorry, I only spoke about gluons because I'm most interested in small X evolution. The glap has both quarks and gluons, and they're equally non-overlapping. Quarks and gluons are produced with higher virtualities, means they have smaller and more transverse areas. So the more you have, the more diluted they are, because the increase in the number is more than compensated by the decrease in the surfaces.
So the gluon concentration is not increasing in D-glap.
No, the gluon concentration is not a well-defined concept, only the gluon occupation number. Having many gluons, which is more enough, doesn't prevent anything.
Whereas in
physics, it's a dilute physics. The more you evolve, you have the more gluons, but they're more dilute.
Okay. And why in D-glap evolution the gluons don't overlap, but in BFK they do?
Well, because BFK is a different way to look at the evolution. You are fixing the observable in such a way to probe always the same transverse scale. So you increase the energy as a fixed transverse resolution. That's a small X limit of the IS. The small limit of the IS is high energy at fixed Q squared. That's not the glap physics. So the same physical process can admit one regime or the other, depend how you fix the kinematics. So BFK physics is not a different physics than DIS. It's just physics of DIS in a different kinematic regime. It's also called the Regi kinematics, the high energy at fixed transverse resolution. So that's Regi dynamics or BFK dynamics. That's the glap dynamics. On the diagonal is the double logarithmic approximation dynamics. Any dynamics which does not hit the saturation scale is dilute. So any diagonal going like that is dilute. Anyone which hits eventually the saturation scale goes to a dense system. There are directions of evolution which are controlled by the external kinematics. But what we're looking at in the physics. They're both there. The wave function has all the visual excitation. The question is what you measure.
Yeah, so I also have a question actually related to this plot, right? So, these PDFs are meaningfully defined concepts, right? In principle, it doesn't matter what path you take in this thing to arrive at a certain location, right? I mean, at least it should, right? You agree? Okay. Then I'm wondering is there a form of sort of modified D-glap evolution also in the saturation regime?
The right statement is that what is called PDFs, the integrated gluon distributions, are only right degrees of freedom in the dilute regime. For this system here, I have generalized PDFs, integrated gluon distributions, which are more than one, and the whole evolution here is written in terms of these integrated gluon distributions or correlation Wilson lines. They reduce to the standard PDFs in the dilute regime. That they're more general than that. So there's no bottom line, there is no modified D-glap applying here. there are modified equations which are different from the glap, which do not contain full glap because we're not able so far to combine full glap and full saturation physics. But the equations which are valid here, when restricted to this limit, they properly reproduce a double logarithmic approximation. The DLA is the only common limit which is embedded in both formalisms. And that again will be manifest later. Okay, so let's thank you for the question. So let's move on. So far, I just wanted to convince you that there is interesting physics associated with high parton density, which come naturally from PQCD, and eventually should be described in terms of PQCD, although I didn't tell you how to describe it here, only here. And here, of course, it was well known. In order to understand how to work that way, we need to understand better what are the degrees of freedom in this high density regime. That's the question I want to start to ask. Can we speak about gluon distributions? We can, but in a loose way, or if we want to be more precise, we have to introduce more specific concepts which goes beyond standard gluon distribution. And in order to introduce this conceptually notions like unrelated gluon distributions, we need first to have a simple physics picture. And the physics picture, you should keep that in mind, is strongly gauge dependent and frame dependent. There is no such a thing as a boost invariant and gauge invariant physical picture. Only the observables are boost invariant and gauge invariant. The physical picture is essentially impossible and obscure in most of the gauges and most of the frames. There are very well-tuned frames and gauges where the physical picture makes sense, at least to our intuitive understanding. So to build that, we have to choose properly the frame and the gauge, and I will start by choosing the frame. You know that, I mean, the parton picture makes only sense in the infinite momentum frame of the parton, of the proton. Otherwise, we cannot speak about partons. And that will be also manifest what follows. So I will move towards the best frame to be used for the high energy evolution. And I'll do that on the example of DIS. So far, I was looking at DIS implicitly in the infinite momentum frame of the proton, in which the whole evolution, the whole parton cascades were associated with the proton wave function, which as small x was developing a gluon cascade, and eventually the less gluon here was splitting in the quark-anti-quark pair, which was measured by the virtual photon. There are several possible frame infinite. There is no unique infinite momentum frame. An infinite momentum frame is any frame in which the longitudinal momentum of the photon is infinite as compared to the mass. The best for the physical interpretation of the parton picture is what's called the Bjorken frame or the Bright frame, in which the longitudinal moment, the virtual photon here, the photon is space-like, so his virtuality is negative. Q squared is a modulus of the virtuality. In the Bjorken frame, the 4 momentum Q mu of the incoming photon here has no longitudinal momentum, so it's a standing wave, has some small energy component and a non-trivial transit component. Why small Q0? Because you see, Q0 is a ratio between the invariant P dot Q divided by P0. P0 is the energy of the proton, and P dot Q is an invariant. In the infinite momentum frame of the proton, P0 is arbitrarily large, whereas P dot Q is a boost invariant. So if I go to infinite P0 limit, then this Q0 goes to 0, because P dot Q is boost invariant, and I keep boosting the proton, P0 is arbitrarily large, so Q0 is arbitrarily small. So in this frame, automatically the virtuality of the photon is dominated by the transverse component, which is why the virtual photon is a good analyzer of the proton transverse structure. So when we speak about the virtual photon as viewing the proton on a given transverse size, that's correct, but only in that frame. This statement makes no sense in any other frame. But in this frame, yes, the virtuality of the photon is just the transverse momentum of the photon. So the virtuality is a boost invariant quantity, but the fact that this is the rate of the transverse momentum is valid only in that frame. So in this particular frame, indeed, the virtual photon measures partons with a given transverse area. And the scattering in this frame counts the number of quarks having this given transverse area. That's a parton picture. Now, the drawback for our purpose is that in this frame, also this quark-anti-quark pair here, it's a part of the proton wave function. But we know that at small x, the evolution involves mostly gluons. So we like to decouple the final quark, which is just a property of the observable, from the evolution, which should involve only gluons. And one can do that easily by just boosting a big backward the proton. See, the proton is a left mover here, the photon is a right mover. I will systematically use this convention. The dense system is a left mover, the projectile, the dilute projectile is a right mover. So if I boost in this way, we mean I decelerate the proton, because the proton was the left mover, and I accelerate the photon. If I do that, then the lifetime of this fluctuation here is increasing in such a way that this fluctuation now can be viewed as a part of the wave function of the virtual photon. So you see, the picture is very much frame dependent. When you say that this QQ bar pair is a part of the wave function of the hadron, I ask you, in which frame? If you tell me it is in this frame, I say I agree. If you tell me that frame, I disagree. In this frame, the gluons are a part of the wave function of the proton. But this QQ bar pair is an excitation of the virtual photon, which before scattering has grown up these fluctuations. And then these fluctuations, which are a part of the photon now, which is a quark-anti-quark pair, a color dipole because it has zero color charge, when it approaches the proton, it scatters of the gluons inside the proton. So now I have to only worry about the gluon distribution of the proton, and I will use the dipole, not the photon, as a direct probe of the gluon distribution. So I just built an observable, which is probing directly the dipole. It's not another observable. In terms of physics, observable boost invariant, the observable is a DIS structure function. But the way I compute is differently. Before I compute the DIS structure function as a scattering of the virtual photon of the wave function of the proton in the infinite momentum frame, now I'm going to compute it as a scattering of the dipole of the gluon distribution in this boosted frame, and I would have to take into account, on top of that, the probability for the virtual photon to decay into quark-anti-quark pair, the virtual photon wave function. And I'll show that in a moment. So, yes, and it is easy to check that the very fact that we're looking at small x, that's the definition of small x, Q² divided by S, or 2p is much more than 1, is tantamount to saying that the lifetime delta t of this quark-anti-quark fluctuation, and I remind you that this lifetime is twice qz divided by q², is much bigger than 1 over pz. So this condition is the same, but in this frame, this condition is just telling me that the lifetime of this QQ bar fluctuation is much larger than the typical scattering time. The typical scattering time was 1 over pz. So this condition is boost invariant, but this rewriting of the condition is a standard in the dipole frame. The QQ bar pair, it's a fluctuation of the photon, which has a lifetime much bigger than the collision time, which means it has been created long before the scattering. That was the same story again and again, that the Lorentz boost is amplifying the lifetime of the fluctuation. Now I have boosted the photon, and now the photon is the photon is now, the photon we used to have zero longitudinal momentum. Now it has a large longitudinal momentum, essentially equal to Q0, and they're both of them much bigger than virtuality, so it's a very energetic photon. This very energetic photon develops well before the scattering, a quark-anti-quark fluctuation, a dipole, and then this dipole has a large lifetime. It exists forever from the point of view of the scattering, and eventually it hits the gluon distribution of the target and it measures the gluon pair. So that is aiming toward the factorization of the DIS process between a fluctuation of the gamma star into a quark-anti-quark color dipole, followed by the scattering between the dipole and the gluons inside the proton. And then if I know the gluon inside the proton, I know how to, and this factorization, I know how to compute DIS in this frame. Now, but I don't have to stop here. So far, the whole gluon evolution is a part of the proton wave function. So the most of the energy is still carried by the proton. Pz is much larger than Qz. So Pz is a longitudinal momentum of the proton, which is a left mover, and Qz is longitudinal momentum of the photon, which is a right mover. So if you want, there's a modulus. Pz, if you want, is negative, Qz is positive, but the Pz here is the modulus of Pz. Okay? So far, since the whole high energy evolution is still in the proton, it means that Pz is much bigger than Qz. So the high energy evolution with the gluon emission is still with the proton. But I can keep boosting the photon. The physics is boost invariant, the observer boost invariant, so I can choose to look at the DIS in a frame in which the photon carry the whole high energy evolution, which means I go to the opposite situation where Pz is much more than Qz. In that case, Pz is just 3 valence quark with approximation. I have no small x evolution. I have the glap, but I don't care. So there is just 3 valence quarks, but all the gluons which were there, they're still in the problem. The gluons don't disappear. What is changing is the physical interpretation. Now all these gluons are a part of the wave function of the dipole. So in this very boosted frame, the photon is highly energetic. The proton is at rest. This is a picture of DIS. That's a picture of DIS in the proton rest frame. There's no parton picture. the proton is just 3 valence quarks with a lot of vacuum fluctuations around. But the perturbative QCD evolution is still there. It's not on the proton side, so it's not a part of the partonic structure of the proton. It's rather a part of the Lycon wave function of the virtual photon. All these gluons now are emitted. This gluon is a most energetic one. This is less energetic, this is less energetic, so X decreases like that. And the less gluon, the less energetic one, with an X of order Bjorken X is a boost invariant, scatters of any of the valence quarks here by a gluon exchange. So by boosting the frame, the system, I can change the physics picture. I can go from the infinite momentum frame or the parton picture of the proton was manifest to a dipole frame where the evolution is fully associated with the virtual photon. You can say that now is a parton picture of the photon which is manifest, and that's correct, except that it's not spoken about in textbooks. In textbooks, by parton picture, one means only the proton. No, that's still parton picture, it's just a parton picture of the photon. And the proton now is just has no partons from the point of view of PQCD. And so far, the evolution is linear. It's just, if you're on BFKL or the GLAP evolution, it's interesting to see what happens when you also have nonlinear physics, which I'll model by this kind of recombination. Now it's not the end of the story, but assuming that this is just recombination. So now, in the frame in which I had the whole evolution inside the proton, then I have a dense system of gluons. They overlap with each other, and then two such gluon cascades can merge with each other and reduce the gluon density. That's a physics of saturation. It's a nonlinear effect in the evolution. So I have one evolution, two evolution, and here's a merging of three evolution. So it's a nonlinear evolution. But now if I boost the frame, this vertex here becomes a splitting vertex here. So now if you look at that, there is no two branches which merge with each other. There are just two gluons in the same branch. So a nonlinear effect, merging, becomes a linear effect, a splitting. But now each of the ensuing branchings are propped by the scattering, because you see, the vertices at which here the branches were emitted by the gluon, by the quarks in the proton wave function, now become vertices at which the gluons in the two different branches are absorbed by the valence quarks in the proton. So the nonlinear physics of the evolution here becomes the physics of linear evolution followed by multiple scattering. And that's very profound, Johan, because see, nonlinear evolution is complicated. Linear evolution is much simple. Multiple scattering is much simpler than nonlinear evolution. So one can describe essentially the same observables, which reflect to this physics, which reflect a complicated nonlinear evolution, by studying much simpler linear evolution followed by multiple scattering. And that's a way I will proceed in practice. That's the way I will build the evolution for you. I will describe nonlinear physics by looking at linear evolution, and I will just insert on top of it the multiple scattering. In particular, the recombination here get mapped onto splitting here, so 2 to 1 gets split, merged into 1 to 2. But here, I went from 2 to 1, but only 1 was measured. Here I go from 1 to 2, but they're most measured. And when you measure both product of a splitting, you measure the fluctuation, measure whole distribution. So gluon saturation in the infinite momentum frame of the proton gets mapped into fluctuation in the evolution of a dilute projectile in the BFKL evolution. It's a deep connection between saturation in a dense system and fluctuations in a dilute system. They're all different sides of the same physics, depending upon the boost. Questions? Okay, so that was a more conceptual issue that will be important for our fellows. Now a much more trivial one, kinematics. Everybody likes kinematics because it's simple. So you already seen that, you're familiar with, but let me just introduce my notation. For describing high energy problems, it's very useful to use Lycon kinematics. So far for me, four momentum P mu had these 4 components, energy, X, Y, and Z. The X and Y, the Z is always referring to the longitudinal axis, or the collision axis. In a proton-proton collision is the collision axis. So I'll keep PZ for the collision axis. I will keep P perp for the 1 and 2 components. These are the component in the plane transverse to the collision axis. So that's transverse means transverse to the collision axis. So it's energy, transverse plane, and longitudinal axis. And then instead of working with P0 and PZ, it is convenient to introduce the plus and minus component. They're defined this way: plus and minus is P0 plus minus PZ divided by square root of 2. And that's valid for any 4 momentum. Except for the 4 momentum position, x mu, the x plus and minus t0, x0, which is t plus minus z, which is x3 divided by square root of 2. The dot product now, it's coupling plus and minus components. So the scalar p dot x product is p plus x minus p minus x plus minus p perp x perp. I use the standard metric of particle physics. And the factor of squares of 2 introduced in such a way to have no factor of 2 in the dot product or in the measure. So the measure dt dz is invariant, is dx plus dx minus. Okay, so why is this, are these 4 momenta, or this lack of variables convenient? So this is a cartoon of the space-time structure, the dimensional axis and the time axis. This is the axis x plus. So along this axis, x plus is increasing, whereas x minus is 0. This is axis x minus. Along this axis, x minus is increasing, whereas x plus is 0. And a collision between 2 ultra-relativist particles coming from minus infinity can be viewed as 2 particles approaching approaching against each other along the lie cones, and which meet at time equals 0 if you fix the initial condition properly. So, for instance, just look at the right mover here, ultra-relativistic right mover. Assuming there is a classical object, a ultra-relativistic right mover has a trajectory which is z equal t, which is in these variables means x plus is t up to a factor square root of time, whereas x minus is 0. So x plus is a time for ultra-relativistic right mover, so it's called like on time. X minus plays the role of longitudinal coordinate, and you see that one can rephrase the statement that the particle is ultra-relativistic, so it has z equal t, as a statement that the particle sits at x minus equals 0. So this Lycon frame is like the rest frame of the ultra-relativistic particle. So that's why it simplifies things. It puts some of the coordinates to 0 because these coordinates are fixed by the trivial dynamics, by the trivial motion. So for the right mover, x plus is time, x minus longitudinal coordinate. For the left mover, the roles are totally interchanged. This is a left mover. In this case, x minus is a time. So the particle progresses along time with time being, where it stays at x plus equals 0. So x plus is the longitudinal coordinate. So from now on, I will always have a scattering. So I have a left mover, a right mover. So what is like on time and what is like longitudinal coordinate depends which I'm looking, which of the 2 objects I'm looking at. If I look at the right mover, it will be the projectile. The x plus is like on time. If I look at the left mover, the target, then x plus is going to be longitudinal coordinate. We have to be a bit careful about that, but I can always restate that. So that's about a classical object with a classical trajectory. Now let's look at the on-shell particle. Let's take it to be a right mover. On shell means that p squared is m squared. Let me take a generic m, but eventually m is going to be 0. P squared is in this Lycon coordinates is twice p plus p minus p per squared. It's an ultra-relativistic right mover, which means pz and p0 are essentially the same and much bigger than the transverse momentum or the mass. And now if I use this Marshall condition to extract from here p plus and p minus, of course, p plus is pz plus p0 divided by square root of 2. P plus and pz are essentially the same, so p plus is square root of type 2pz, it's big. Whereas p minus essentially is 0. Why? Because p minus, as you see from this condition, is m squared plus p per square divided by 2p plus. And since p plus is much bigger than p per m, this p minus is much smaller than the square root of the denominator, which in turn is much smaller than p plus. So I have an hierarchy. For on-shell particles, which is ultra-relativistic right mover, the p plus component is the largest one, the transverse component or the mass is the intermediate one, and the minus component is the smallest one. The p plus component, obviously, the longitudinal momentum is a big component. The p minus is called Lycon energy. Why? Because it is coupled to the Lycon time in this dot product. So minus is coupled to plus, whereas plus is coupled to minus. So there's natural to be this to view this as longitudinal momentum because it's coupled to the longitudinal coordinate. Plus is longitudinal momentum is minus longitudinal coordinate for the right mover. Vice versa, x plus is the time for the right mover, and p minus longitudinal energy because energy is coupled to time. And in the first approximation, ultra-relativistic right mover has a p plus, a big p plus, and no p minus, and it can have a p perp or not, depending on what you're looking at. But even it has a p perp is much more than p plus. Using this Lycon variable, it is also convenient to redefine the longitudinal momentum fraction as being not a fraction of pz, but a fraction of k plus for the right mover, or of k minus for the left mover. Right? That should be very careful. That's for the right mover. So x is, if I have a proton with longitudinal momentum p plus, which is a proton which is right mover, which is motion momentum P+, and I took a parton inside the proton with motion momentum K+, the motion momentum fraction of that parton inside the proton is K+ divided by P+, not Kz divided by Pz. Why? Because with this definition, this value of X is boosting the Ayan. The one which is the ratio of the Z momenta have not been boosting the Ayan. You can check that easily. So from now on, motion momentum fraction refers to the Lycon variables. It's a fraction of K+ for a right mover. It's a fraction of K- for a left mover. K+ motion momentum for a right mover, K- motion momentum for a left mover. And still at the level of notations or kinematics, I'll also introduce rapidities. Probably you've already seen that in the previous lectures. Let me just introduce the notations because they're very useful in what follows. The rapidities are naturally defined for on-shell particles. So again, I look at the on-shell particle with this 4 momentum in the standard notation, E, P perp, and Pz, where E is the on-shell energy, so the sum of m squared, P per squared, and Pz squared. And the rapidity y of that particle is defined as 1/2 log of P plus divided by P minus, where P plus is again P0 plus Pz, but P0 is on-shell now. By construction, you see, for a right mover where Pz is positive, this is positive, y is positive, while for a left mover where Pz is negative, this is negative because if Pz is negative, the numerator is more than the denominator, then y is negative. And given the definition of the rapidity and the relation between the energy and on the on-shell definition of the energy, one can easily check that the energy is what's called the transverse mass. The transverse mass, I define it here, is square root of P per square plus m squared. So the energy is the transverse mass times the cosine hyperbolic of the rapidity. The Pz is the transverse mass of the sine hyperbolic of the rapidity. You see if rapidity is negative, Pz is negative, that's for the left mover. And the Lycon components, plus and minus, are simply the transverse mass divided by square root of 2 times the exponential of plus or minus eta. So should be y, sorry. It should be y. Eta and y will be the same eventually, but for the time being, that's just a misprint. Should be y here. Just extract this one. Now, why is the rapidity convenient? Rapidity is convenient because it transforms simply by a shift at the Lorentz boost. So if you make a standard Lorentz boost with velocity beta and a factor gamma, then the rapidity goes from y to y plus a constant which depends upon the boost. So the rapidity transformed by a shift. And now, this quantity is important conceptually because it's transformed by a shift under Lorentz boost, but it's not directly measurable in the experiments because in experiments they don't measure the energy of the particle, they measure the longitudinal momentum, right? They measure the propagation angles. So there is also what is called the pseudo-rapidity. The pseudo-rapidity is a measurement of the propagation angle theta of a particle with respect to the collision axis. So the formal definition is 1/2, it's like here, but we replace the energy, only energy, by the modulus of the 3 momentum. So if the mass is non-zero, E and P are not the same. And if you want, the relation between eta and the propagation angle with respect to the collision axis is given by this expression. The propagation angle, the cosine theta is Pz divided by P, and sine theta is P per divided by P. I will show that. Sorry, I'll show that on a figure in a second. What is important for us follows that if you neglect the mass of the particle, then the modulus of P and the energy are the same, and then y and eta are the same. So in what follows, I will systematically neglect the masses of the particles. So I will speak indistinguishably about rapidity or pseudo-rapidity. They will be the same for the purposes. And I will always use the notation eta for definition, for definiteness. So this relation is also correct for in terms of eta, provided the mass is 0, so then m perp is just p perp. Okay. So I think I will stop here because I just introduced for you let me just show a simple cartoon where the angle appears. So that's a scattering between a proton and a nucleus, and that's the produced particle after the scattering. And you see theta is the angle made by the produced particle with respect to the collision axis. And a nice definition of this theta, instead of working with theta directly, one can work with theta directly, of course, but the experimentalists, for good reasons, prefer to work with a pseudo-rapidity, which is related to this eta, by this expression from here. So eta or angle is the same. Y is not the same as an angle, but it becomes an angle if the particle is massless. So in what follows, particle will be massless and y is eta the same. Okay, so I'll stop here. I'm way back what I was trying to do today, but it doesn't matter. The time is over, so question, please.